Good morning, girls. Today we are going to see about trees and fundamental circuits in graph theory. So it occurs in Unit 2, Chapter 3. Okay, trees and fundamental circuits today. In this, what about the definition of trees, some properties of trees, distance and centers in a tree, and theorem related with the center are going to discuss in this class. Okay. Now, definition of tree. What is definition of tree? A tree is a connected acyclic graph. Acyclic means no circuits. So, a connected graph without any circuits is called a tree. Okay. A connected graph without any circuits is called tree. So, see the graph tree, example tree. Here we have a tree with nodes. Nodes means vertices, and edge means here branches. U is denoted as node, that is vertex, and X is denoted by the branch. The edge is denoted by branch. Okay, tree looks like a tree. So, tree is what? Connected graph without any circuits. Connected graph without any circuit is a tree. Looks like a tree, isn't it? Okay. Next, we have some properties we may discuss. Before that, we have some note. We may observe some points from the tree. So, the edges are known as branches. A tree with n vertices has n-1 edges. See here, some examples are here. Tree with 1, 2, 3 and 4 vertices are displayed here. So, if it has one more edge extra than n-1, then the extra edge should obviously what? Has to pair up with the two vertices, which leads to form a cycle. So, it cannot be occur in a tree without circuit. So, tree with one vertex, just vertex, one vertex. Next, tree with two vertex, just one edge. Two vertex but one edge. So, and see the next one, three vertex but two edges, two branches. Next, four vertices, we have only three branches. Okay, so n vertices has n-1 edges. So, a tree with n vertices has n-1 edges only. Okay, we should observe these 2 points. Next, we have another note, that is every tree has two vertices of degree 1. Every tree has at least two vertices of degree 1. See that here the tree with the 4 vertices A, B, C, D. So, it has two vertices of degree 1. What is that? Vertex A has degree 1 and the last vertex D has only degree 1. In between two vertices B and C, degree 2. So, every tree has at least two vertices of degree 1 only. Okay. Then next, some properties. You may going to see some properties of trees. So, some properties are here stated as theorem. So, first one, there is only one path between every pair of vertices in a tree. Or there is only one path. There is only one path between every pair of vertices in a tree. See the figure. We have the vertices A, B and 1, 2, 3, 4. So, there is a path between A and B. A to 1, 1 to 2, 2 to B. And another path A to 1, 1 to 3, 3 to D. So, two paths here. If two paths exist means we have a circuit. What is that circuit? 1, 2, B, 3, 1. That will be what? It will become a circuit. So, it cannot be possible. So there is only one path between every pair of vertices. So theoretically, we have, since T is connected graph, there exists at least path between every pair of vertices. Connected means every pair of vertices connected. That is a path between every pair of vertices. Now suppose between any two vertices A and B of T, there are two distinct paths. If suppose there are two distinct paths, then the union of path, two paths, will contain what? A circuit. Then T cannot be a tree. So tree means circuitless connected graph. So in which there is only one path between every pair of vertices. Okay. Next, converse part. It is stated as theorem 2. If in a graph G there is one and only one path between every pair of vertices, then G is a tree. Converse of the previous theorem. So see the graph tree, and theoretically we have existence, we can prove the theorem, existence of a path between pair of vertices. Assures that G is what? G is connected. For every pair of vertices, if we have a path means G is connected. Next, a circuit is a circuit in a graph. That means what? With two or more vertices. Implies that there is at least one pair of vertices A and B, such that there are two paths between A and B. Circuit. A to B, one line, and we may reach from A to B in another way. So joining the path, we get what? Circuit. So G has only one path between every pair of vertices. That is, G has no circuit. Then G is what? G will be a tree. G will be a tree. Okay. Next, we have another property that is stated as theorem 3. A tree with n vertices has n minus 1 edges. Already we discussed in note point 3. It is given as theorem. Now, a tree with n vertices has n minus 1 edges. Okay. See the example. Tree with 1 vertex, 2 vertex, 3 vertex, 4 vertices are given. So from this we can trivially to the theorem with n vertices means n minus 1 edges. Next, another example. Let us consider a tree with n vertices. In T, consider the edge EK. EK means what? EK be the edge with n vertices VA and VK. So in this there is no path between VA and VJ except EK. We have deletion of EK from T will disconnect the graph. Therefore, if we have T minus EK consists of exactly two components. T minus EK consists of exactly what? Two components. And since there are no circuits in T, begin with each of the components is a tree. But both of these components, T1 and T2, has fewer, less than vertices than T. Less vertices than T. And therefore, by the inclusion, by the induction hypothesis, each contains one less edge than the what? Number of vertices in T. So T1 has number of vertices less than T, and T2 also contains what? Number of vertices less than T. Therefore, thus in T minus EK, thus T minus EK, come to original T, original tree, delete EK. in T minus Ek consists n minus 2 edges or n minus 2 edges. Hence, T has exactly n edges. So, we can prove T with n vertices has n minus 1 edges. Okay. Next, it is another converse part. It is stated as theorem 4. Any connected graph with n vertices and n minus 1 edges, just any connected graph, n vertices and n minus edges, n minus 1 edges is a tree. It is converse of the previous one. Okay. How we prove it? Trivial one. We know that the minimum number of edges required to make a graph of n vertices connected means we need what? Minimum number of edges is n minus 1 edges. So we observe that if we remove one edge, removal of one edge from the graph G will make disconnected. Removal of one edge from the connected graph makes what? Disconnected. So thus a connected graph of n vertices and n minus 1 edges cannot have a circuit. So if a connected graph no circuit means what? It is a tree. Hence G is a tree. Okay. So any connected graph with n vertices and n minus 1 edges is a tree. Okay. Next, what is minimally connected? We have one definition, minimally connected graph. So a connected graph is said to be minimally connected if removal of any one edge, at least one edge remove means it disconnected. Removal of one edge from it disconnects the graph. That is minimally connected graph. So we may combine the term minimally connected graph to the tree. So it is stated as theorem 5. So a graph is a tree if and only if it is minimally connected. Okay, a graph is a tree if and only if it is minimally connected. How do we prove it? Proof. A minimally connected graph cannot have a circuit. Why? If you remove one edge, then it will be disconnected. So a connected graph is said to be minimally connected if removal of any one edge from it disconnects the graph. So in that minimally connected graph, we cannot have a circuit. Otherwise, if its circuit means what happened? Otherwise, removal of one edge in the circuit and still leave the graph connected. Thus, a minimally connected graph is a tree. Okay. Conversely, if a connected graph G is not minimally connected, then what happened? Then it not be a tree. If connected graph is not minimally connected means then it is not a tree. How? Not minimally connected means what? There must exist an edge E I in graph G such that G minus EI is connected. So if you remove one edge, it cannot be disconnected means what is that? It is not minimally connected. So not minimally connected means there must be an one edge EJ in G such that G minus EJ is connected. Therefore, EJ is what? Is in some circuit. So it tied up. It is linked in a edges. So it is in circuit, which implies the graph G is circuit means what? It is not a tree. Okay. So not minimally connected means it is not a tree. Therefore, a graph is a tree if and only if it is minimally connected. Okay. Next, another property, a graph G with n vertices, n minus 1 edges and no circuits is connected. So see the statement, n vertices, n minus 1 edges and no circuits, it will be what? Connected. How it is connected? Proof. Suppose that there exists a circuitless graph G with n vertices and n minus 1 edges. but which is what? Disconnected. We take circuitless graph with n vertices and n minus 1 edges, which is disconnected. So in that case, G will consist of two or more circuitless components. G is disconnected graph, so it will have more components. So without loss of generality, let G consist of two components, G1 and G2. Two components, G1 and G2. Add an edge E between a vertex V1 in G1 and another vertex V2 in G2. Add an edge between these two vertices. Since there was no path between V1 and V2, V1 in where? V1 lies in G1, V2 lies in G2. Both are disconnected components from G. So there was no path between V1 and V2. Now adding E did not create a circuit. So it will not affect the circuitless property. So E did not create a circuit. Again we have a circuitless only. So thus G union E is a circuitless graph, connected graph of n vertices with n minus 1, n vertices with n edges. Is it possible? Which is not possible. Why? We have what? Tree with n vertices as n minus 1 edges. Hence, circuitless graph with n vertices and n minus 1 edges only what? Connected. Can you understand? If you take disconnected, we have a contradiction for the vertices n and edges n minus 1. So disconnected means we have only what? Connected graph of n vertices and n edges, which is not possible. So contradiction. Hence only what? N vertices with the n minus 1 edges and no circuit means it must be what? Connected graph. Okay? Very important theorem. Next, so far we seen 5-6 theorems, and adding all the theorems we obtain a condition for a tree. Condition for a tree. What is the condition? A graph G with n vertices is called a tree if we have 5 points. A graph with n vertices is called a tree if G is what? Connected and is circuitless. First aspect definition. Next, G is connected and has n minus 1 edges. So it is one of the theorem. G is connected and n minus 1 edges. Otherwise, G is circuitless and has n minus 1 edges. And fourth result also stated in theorem, there is exactly one path between every pair of vertices in G. There is exactly one path between every pair of vertices in G. Or otherwise, the last theorem, which is stated as G is minimally connected graph. So a graph G is a tree with n vertices. A graph G with n vertices is said to be a tree if G is minimally connected. So all these 5 points give the definition for a tree, condition for a tree. That means a graph with n vertices is said to be a tree means we have what? What are the points? G is connected and is circuitless, and G is connected and has n minus 1 edges, and G is circuitless and has n minus 1 edges, and there is exactly one path between every pair of vertices, and G is a minimally connected graph. Okay, these are the condition for a graph with n vertices to be a tree. Okay, next we see that pentagon vertices. Pentagon vertices in a tree. What is pentagon vertices in a tree? See, a vertex of degree 1 is called pentagon vertex. Vertex of degree 1 is called pentagon vertex. So already we studied in a tree there are at least 2 pentagon vertices. In node point we studied. Now it is stated as theorem. A tree, 2 or more vertices. There are at least 2 pentane vertices. Okay. Proof. In a tree of n vertices and n minus 1 edges, what is total degree of the graph vertices? Total is 2 into E. E means edges, number of edges. So 2 into n minus 1 degrees. In that graph, we have in the tree, we have 2 into n minus 1 degrees for the vertices. It will be divided among these n vertices. In a tree of n vertices, n minus 1 edges. So whatever the degree of the vertices means, total number 2 into E, number of edges. That is 2 into n minus 1 degree for the tree. So for the tree, 2 into n minus 1 degree must be divided among all these n vertices. So no vertex be of degree 0. We have what? No degree has a degree, no vertex has a degree 0. So there are at least 2 vertices of degree 1 in a tree. So 2 into n minus 1 degrees to be divided among all these n vertices. So again one point is there, in a tree no vertex is of degree, it is a connected graph, so no vertex having degree 0. So there are at least 2 vertices of degree 1 in a tree. Okay. So it is one of the theorem using pentane vertices. Regarding pentane vertices in a tree, we have this theorem. Next, another concept, distance and centers in a tree. So distance and centers in a tree. We may calculate the distance between vertices and the center of a tree. What is distance between vertices and the center of a tree? See the tree A, B, C, D with the 4 vertices. See that in this, by looking at a tree, the vertex B is in center. By visual we can able to guess center of the tree is what? B. And what is the distance concept? Come to the definition. In a connected graph G, distance D of distance between 2 vertices Vi, Vj is what? Length of the shortest path. Length of the shortest path between Vi and Vj. So what is distance? Length of the shortest path between Vi and Vj. Okay. Again, another concept we have, eccentricity. Eccentricity. So the eccentricity is denoted by E of E of a vertex small v in a graph G is the distance from V to the vertex farthest from the V. Distance farthest from the V in G. That is E of V equal to maximum of D of V comma Vj. Maximum of D of V comma Vj. So a vertex with the minimum eccentricity in a graph G is called center of G. So what is center of G? Vertex with the minimum eccentricity is called center of G. See that our tree in this eccentricity of A. So we can calculate A lies here, B, C, D. So the distance from C to A is 2, distance from D to A is 2. So eccentricity of A is what? 2. And eccentricity of B is what? Again 1. So we can reach B from any vertex, C to B, D to B, A to B. We have only one edge. So the length of the path is what? Only 1. So distance is 1. So eccentricity of B equal to 1 only. Next, eccentricity of C. So to reach C, we have the path. So we have 2 edges. To reach C, we have 2 edges. So eccentricity of C is 2. Similarly, D. eccentricity of D equal to 2. Hence, the minimum eccentricity is what? Having only B. The minimum eccentricity for which vertex? Only B. E of B equal to only 1. So, therefore, the center is what? B. The vertex B is center of a tree. Center of our tree. Okay. Can you understand the distance, that is distance between two vertices from which we can identify the eccentricity of the vertices, again center of a tree. So, three concepts we discussed here: distance, eccentricity and center of a tree. Okay. Next, we have another example for a center is discussed here. For another graph, using another graph, we have discussed distance of V1, V2. See that it is clear the definition of distance between two vertices is valid for any connected graph, not only tree, for any connected graph, connected graph with the circuit. So, we have a with the loop, everything. We have a same concept, distance definition for the distance. Okay. So, see the graph and find out the distance between two vertices V1, V2. Okay. Graph is given and the path between vertices V1 and V2 is discussed here. So, V1, V2 can be reached by considering the path, that is A, E, and another path A, C, F, and another path B, F, and another path B, G, H, and another one B, G, I, K. So, among these we have two shortest paths. What are they? One A, E, another one B, F. So, only length of two shortest path. So, hence what is our distance between V1, V2? Vertex V1 and V2, distance between V1 and V2 is what? Only 2. Okay. Next, now the important theorem related with the center in a tree. So, what is the theorem? Every tree has either one or two centers. Every tree has one or two centers. Now, proof the maximum distance we calculate. How we calculate? We can calculate the maximum distance between vertex V and the farthest vertex Vj. From a given vertex V can be taken what? From a penton vertex we can calculate the distance. So, in a tree, let us consider the tree in the figure, tree T. Tree T must have what? Two or more penton vertices. So, see that penton vertices. So, the distance of every vertex is given here. So, the first vertex is given as degree 6, second 5, the bottom 5, and upper penton vertices distance 6, 6, 6, and in between 3, the 3 minimum eccentricity, that is the center. 3 minimum eccentricity 3 is given. So, that vertex is what? Center vertex C, denoted as C. Then next 4 distance is 4, 5, and penton vertex 6. So, penton vertex given. So, and the corresponding distance also mentioned in the T. Now, if you delete all the penton vertices from T, that will give out T dash. See T dash. In T dash, we delete the penton vertex. For all the penton vertex, only we have this T dash. Can you understand? T dash. In T dash, what is the center? See that center, the distance is only 2. That is. Again delete all the penton vertices. Then again give what? T double dash. Continue this process until we arrive either a vertex or an edge. Can you understand? Delete all the penton vertices every time. Delete all the penton vertices until how? When we arrive one vertex or an edge. Here we arrive one vertex, that C. Point C, vertex C is arrived here with the distance what? 0, only one vertex. Okay. So, in a tree, every tree has what? Either one or two centers. Here we have only one center. Okay. Very important theorem. Having binary trees later. Next class we may see binary trees and spanning circuits. Okay. Good. Understand, every tree must have either one or two centers. Very important theorem in this class. Okay. Thank you.